So we spent quite a bit of time in the class so far working on how to build a terrain and build a mesh and add boundary conditions. And we're finally ready to actually put that all together and run a model. And so that's what we're going to do in this workshop. We're going to create a simple model. And so like with a lot of the workshops in this class, we're going to have you just start from nothing. You're going to actually create a model and just go one more time through each of the steps of getting to a model. So we'll come here and we'll say File, New, and we will create a new project. And we're supposed to call it Creating a Simple 2D Model. And so we get this title, but then from that title, it creates a file name. Now, that may or may not be a file name you want. I think maybe just Simple 2D. You'll notice that it runs out of characters at some point. And so we're going to call it Simple 2D there. And so this will be the title, but that's the file name, which all the other files will inherit from. So then, yes, this is going to be in US customary. Apologies again to those who don't prefer those units. And so the first thing we're going to do is go get a projection. So we'll set our projection. We will go to GIS data, and then this is our projection. All right, we're all set. And then we're going to make our train, and you can of course go to File, Create New RAS Train, but I just right click on the train here, go to Create New RAS Train. We're going to add our train data, and let's add both of those. And this is the channel. This is the overall DM, so they came in the right order. If I wanted to switch them, I could, but I don't. And so we are going to create this train. So now we have a train, and this is called the Bald Eagle project. This is one of the standard example data sets in RAS. You'll become very familiar with this project if you work through the class. And so now we're going to create a geometry. So we'll come in here and create a new geometry, and we'll call this simple model. And then we'll edit. We have a map here of where we want our boundary conditions and what our model domain is going to be. There is a dam in this domain. If we zero in on here, here's the dam, and then here's the spillway. And so, what we're doing is we're actually kind of setting up a model downstream of the dam, and eventually later in the class we'll go ahead and fail the dam and look at a dam failure model. But for now, we're just gonna actually just run flows out of the dam and look at downstream flooding. And so we could go in, we're gonna start editing, and we're gonna go select our perimeter, and we could go in and just start digitizing, but we actually have a digitized perimeter that we're going to bring in a shapefile. So I'll come in here and I'll say import features, and we will go again to our GIS data where we have our boundary shapefile, and we'll import it. And so now that just imported a shapefile that is our domain. So the next thing we're going to do is we're going to go and we're going to edit that domain, and we're going to use pretty big cells here. And one of the reasons we're going to start with what are really big cells is then we're going to refine them and see what effect it makes. So we're going to start 500 by 500. For a domain this size, 500 by 500 is pretty big, but we're just trying to learn here. So we'll make the n value 0.04, and we will generate computation points. And so you can see that we've got about 2,000 cells. Then it also tells you the average face length. That's going to be pretty close to 500. It's not going to be exactly 500 because there'll be some corners, but that's kind of what we're looking at there. We can turn on the computation points, and what we're looking for is red computation points to see if there are any errors. And it doesn't look like there are. In your model, there might have been. So now the next thing we need to do is we need to add our boundary condition lines. Now we're going to add our boundary conditions in the flow editor, but we need boundary condition lines in the model in order to tie the flows to them. And so we need the boundary condition lines in the geometry. This is one of the big differences in RAS 2025. In RAS 2025, the boundary conditions are georeferenced in the flow data themselves. But here we actually need to tell the model where in the geometry the boundary conditions are. So we'll come here to boundary condition lines, and we've got several boundary conditions. One is just kind of downstream of the dam. And so that's going to be our main boundary condition. Now we're only going to go from here, and I'm going to call that inflow. Now why didn't I go all the way here? Well, that's a spillway, and so the spillway really should get its own flow. Otherwise, we would take the flows here and we would put it down the spillway. So we want to kind of constrain where our flows are. And then we've got a couple of tributaries right here. We've got we've got Marsh Creek, and we've got Beech Creek, and then we got just one more like side channel, which is Fishing Creek, and then we have our downstream boundary condition. And so then we can stop editing. And the next thing we need to do is a little counterintuitive. We actually have to open the geometry editor. So we can go to Edit, Geometric Data, or we can just push this little stick figure here and open the Geometric Data Editor. And what we need to do is we actually need to go and open the geometry we just made. And that's a little counterintuitive because we just made a geometry. It seems like it should show up in the geometry editor, but these are two different kind of tools that were developed in different times, and so you just have to get them to talk to each other. And so we open the geometry in the geometry editor, and now if you go to the unsteady flow data, and so you can go either to edit unsteady flow data, but eventually you're just going to push the buttons. And these three buttons here, these are the flow buttons. You got steady flow, quasi-unsteady, which is really just for certain types of sediment transport, and then unsteady flow is the hydrograph. So we're going to choose that. And you get this unsteady flow editor. Okay, so let's start with downstream because that's going to be the easiest. We're going to use a normal depth boundary condition, which means we're going to use Manning's equation to compute the stage from the flow. And so it just asks us for essentially a friction slope. Well, where are we going to get that? Well, you can get this from measuring the bed slope across the boundary, but here we actually know it. We're going to say 0.001. Okay, well, that was the easy part. Now we need to define 4 flows. How are you going to define these flows? Well, what we have is we've actually got flow data. If you go into your project, you can see there's flow data. And it's this file called simple2D flow modelflows.dss. Now, if you spend much time in HEC software, it's worth knowing what DSS is. DSS stands for the Data Storage System. And it was a way that HEC developed to store time series back when it was kind of difficult to do that. And so we store time series data in DSS. And the cool thing about DSS is that all of our models write to and read from it. So these DSS flows come from HEC-HMS, our hydrologic model. And so you can run the hydrologic model, it outputs a DSS file, and then you can use that DSS file as your inputs for your RAS model. It takes a little bit of getting used to DSS. We actually have a dedicated tool to interacting with DSS data. This is really powerful. This is called DSS View. And if I go and I open my DSS data, you can see that each part of this DSS file has what we call paths. And the path names tell you what the boundary condition is, what kind of data it is, the time step, what time period it spans. And you can come in here and you can plot it, or you can choose more than one and you can plot them. And then you can actually get a table of the time series. And so this is the Beech Creek time series that we could actually copy. And so if we go back into our model and we go to Beech Creek, you'll notice that there are 2 ways to enter data. There's this manual data entry, and it can have a fixed start time or a simulation time. And then there's this DSS reader. And so we're going to use the DSS reader, but I would just want to show you how the other one works. We have a fixed start time because we know when this starts. So we're going to come in here, and we're going to say fixed start time, 29 December 1998. And then that is at 2400. And so that would be the same as 30 December 1998, 0000. Those, basically when the clock hits midnight, it rolls over. It could be either one. And then we have data here every 15 minutes. So if I switch this to 15 minutes, then I can come here, Control V, and copy these data in there. And so you actually have to close it and open it so it saves. But then if you say plot data, you have your hydrograph in there. And so that's fine. But a lot of people like to use DSS because you can just pass the DSS file back and forth. It's a standalone database of the flow data. And so what we're going to do is we're actually not going to use this. We're not going to enter table. We're going to go up to read DSS before simulation. And if we go to select path and file and we enter the DSS data, you can see that we have these different paths for the hydrology output for each of these. So I'm going to go to Beach Creek and I'm going to say OK. So what if you don't have DSS View? How can you look at these data? Well, we actually have a little DSS viewer / editor. It doesn't do nearly what DSS View does. DSS View, you can do all sorts of hydrologic statistics. You can do interpolation. There's just a lot of very cool analysis tools that you can do with time series in DSS View. But we have this kind of DSS Lite right here in RAS that you can open up and you can visualize and do some minor editing on your DSS data. So if you say show plot and you go select something, you can look at, not only what is that hydrograph like, but how does it plot with the other hydrographs that we're looking at. Okay, so we've put that in. We remember it's a 2D model. And so the one other thing that we need to know is, these flows are coming in across multiple cells. And so the question is, well, how much water should be in this cell and how much water should be in this cell? The model has to make that decision. And so the way the model is going to make that decision, it's going to compute conveyance across each of those cross sections and divvy up the flows. But to do that, it actually has to know the friction slope along that. So we're going to have to define the friction slope, even if we define the hydrology with DSS. And then I would always choose tailwater check because that's just generally best practice and it'll keep you out of trouble. Okay, so then let's quickly go do the other ones. I'll do Marsh Creek. I'll choose flow hydrograph. I'll choose the DSS. I'll choose Marsh Creek. If I want to plot, I can. There it is. Okay. And then 0.001 tailwater check. We'll go get Fishing Creek. Same thing. Fishing Creek. 0.001 tailwater check. And then finally the inflow. We'll go to the flow hydrograph. Outflow. And you see that actually, by choosing that, it switches the toggle to that's your main data. You can come back to enter table, but then you'd have to go back. And then 0.001 tailwater check. Okay, so now we have all of our flow. We can save our flow data as. All right, and so then we have a geometry file. We have a flow file. What we need now is a plan file. We're going to open up our plan file, and we'll call this simple plan. And you'll notice that you get prompted for a second title. You have to have a plan name, and then you have what we call the short ID. The idea behind the short ID is if you want to give these things descriptive names, and sometimes the descriptive names get quite long. And so the 16-character short ID, we'll let you go up to 64 characters, but we'd rather you kept it to like 8 characters. Something pretty simple that actually identifies the plan, because we're not going to give you this long title in charts. When we kind of identify something in charts, when we put these things in a legend, we want the identifier to be short. And so that's the idea behind the short ID. So we'll call this simple. Okay, we are going to run the geometry preprocessor, and we're going to run the unsteady flow simulation, and then we're going to give it what we call a simulation time window. And we're going to run from 02 January at time 0, which is midnight of the previous day, to 06 January 1999, again to midnight of 05 is how that works out. All right, and so then we can press compute. Let's see how it goes. All right, so that took about 16 seconds to run. Let's go take a look at it. Okay, and I'm going to turn off the 2D flow area so we can see this. And then I'm going to go look at the result. And you'll notice that it comes back on because the geometry is reproduced in the result. And I'm going to go and I'm going to turn on the depth. And it automatically defaults to the maximum depth. So this isn't any time step in particular. It's the maxima at each cell. But we don't want that. We want to actually look at it over time. And so essentially this time 0 will give you the max. But then as soon as you go to time 1, then you can start animating. And what do you notice? Well, one thing that you might notice is that if you zoom in, that in these first few time steps, the water actually doesn't fill the whole channel. And that's because the way that 2D hydraulics works is that we actually start dry and then we fill the channel from time 0. And so if you don't use a warm-up time or an initialization time, basically the model will have to use the first few time steps to warm up. And so what we're going to do is we're going to come in here, and we do need to make some explicit choices about our time step. This turns out to be a pretty stable model, so this is going to work okay for now. But we'll look at that in the next workshop, the model refinement workshop. We're going to go to options, computation options and tolerances, and there are really two ways that you can warm up or initialize your model. You can have number of warm-up time steps here, and that works out pretty well, especially if you want everything to warm up together, your 1D and your 2D model together. But we don't have a 1D and a 2D model, so what we're going to do is we're going to come over to initial conditions time, and we're just going to give it 24 hours to initialize. And what that'll do is it'll run time step 0 for 24 hours. And in fact, it'll take 10% of that, so 2.4 hours, to slowly ramp up to whatever the flow is at the first time step, and then it'll hold it for 24 hours. It'll let out that first time step, which should allow the water to kind of creep through your model. The other cool thing about that is that it's those early time steps where the flow is wetting your model that can be the least stable. So that will allow your model to work through some of that initial instability before you get any results. All right, we'll say OK, and now we'll run again. And so what you'll notice is that you have this negative simulation time here as it counts down from 24 hours, and then it switches to positive as it counts forward. And so that's how you know when you're in the initial conditions time versus the regular simulation time. And that took 14 seconds to run. And so now if we go look at our model, what does it look like at time 0? Well, at time 0, we've got flow all the way through our model. And if I go in and turn our geometry on, what you'll notice is that, even though we're using pretty big cells, we're resolving channel flow. Well, why are we doing that? Well, there again, that's where we're seeing the advantage of subgrid bathymetry, because this isn't just a computational cell that's computing from, say, this cell center to this cell center. In order for the water to move from this cell to this cell, it actually has to pass this face, which is a cross section. And we can actually look at this face and see what the subgrid sees. If we go to plot property table and we go to profile, we can see that RAS is seeing that as a cross section, that there's a cross section across here that is moderating flow, and then we interpolate from this cross section to this cross section in order to get the channelized flow at a scale much smaller than the cell size itself. And so that's a brief review of the creating and running a simple model workshop. There's a second half of this workshop where we're going to go in and refine the model. We'll play around with cell size, we'll play around with time step, we'll play around with break lines to move from this kind of simple model that I actually, despite the subgrid, wouldn't necessarily give to anyone, to something that's a little bit more robust and start comparing results. I'm Stanford Gibson, the Sediment Transport Specialist on the HEC-RAS team, and these videos were funded by the H Agency SET program.